The next talk is also about mobile networks. It's cracking GSM encryption by Karsten Nohl. I'm looking forward to this talk.
Hey, good morning, everybody. Pleasure to be here at DeepSec in Vienna, and happy to talk to you about yet more GSM vulnerabilities. If you weren't convinced enough of the last talk yet that GSM is an inherently broken technology as it's deployed at the moment. I'm a cryptographer, so I'll be discussing with you vulnerabilities on a different level than the application level exploit we were just looking at. That is the encryption that is supposed to secure all the text messages, voice calls, and whatever other data goes over a GSM network. The point I'll be trying to get across is that GSM's encryption is outdated, very much so. It's old, and has never meant to be a very strong encryption, and by today's standards, it's just not good enough anymore. At the same time, though, it is extensively being deployed for more and more security applications. So there's a big discrepancy between reality and perception here. And I'll be discussing a project that we kicked off earlier this year in which we want to publicly demonstrate how broken GSM is. And I'll need your help on this, but we'll get to that in a bit. So GSM as a technology is what I think the most widely deployed security technology in the world. The majority of humankind is using it in almost all countries of the world, but it's an old technology, and it has a long track record of being broken, just never enough, so it's not being used for security-related applications anymore. The history of attempts to publicly show that this is broken goes back to almost when we first knew what encryption is being used in GSM. At first, this was a secret cipher, but it was then disclosed through reverse engineering. And just a few years later, people already had very potent decryption functions on the cipher itself. For many years, though, they were breaking the cipher itself and not the cipher as it's being deployed in GSM. So we had hints, academic hints, that there might be problems with A5, the cipher, in GSM, but nobody could actually show that. A little later then, people started brute forcing A5, because not only is it a weak cipher, it also uses a small key, a too small key by today's standard. Brute forcing still is possible and has always been. It's just very expensive, and it could be argued too expensive to actually allow practical attacks. So we're talking about something like 100,000 computing years to decrypt a single text message or voice call, which clearly is too expensive for most scenarios. And then finally, people applied some good crypto analysis knowledge and deployed time memory trade-offs, and finally found solutions to practically break GSM in the real world. Supposedly, even back in 2003, people computed those tables that we'll be discussing a lot throughout this talk, but they were never released, and there's doubt that they actually finished computing them. Then again, 2 years ago, a hacking group set out wanting to compute this table to finally show how broken the technology is. And just a very short step from being done and wanting to release these tables, they decided not to because of intimidation and perhaps some commercial interest mixed in there. So now what I'm presenting to you today is really redoing what has been done before with a few tweaks that make it perhaps more practical, but with the one very important tweak, that is community involvement. So as much as I'm presenting this to you today, this is not my project anymore. We handed this over to the community several months ago, and there's nobody in control of the effort anymore. So this really is something that cannot be stopped anymore, as the efforts before were. So the public break attempts have failed, and creating thereby a false perception of GSM security. If so many people have tried breaking it and nobody actually got around to a public exploit that people could use against their own data, they can test against their own system, it must be secure, right? Well, we set out to finally show that that's not the case, and the motivation for that mostly, at least my motivation, is to point to a large problem that's existing with GSM, that is this technology already being exploited by agencies, criminals, law enforcement. The very technology I'll be discussing with you over the next few minutes has been implemented commercially a number of times, and there's a very competitive market, in fact, for selling decrypt machines. They come in several flavors. There's one more obvious attack vector. Everybody who attended David Burgess and Harold Welder's workshop 2 days ago heard in length about these devices. They're called IMSI catchers. The idea being that you can just pretend to be a network and thereby attract a target phone to connect all the calls through your base station. Now that, of course, gives you the ability to listen in on everything they say and read all the text messages they are sending. The drawback would be that you do put yourself out there by actively sending on radio frequencies that aren't yours. You are interfering actively with the victim's phone in ways that they could detect if they pay attention. So while this is the more common form of cracking GSM, it's perhaps the least elegant one, since it is very much detectable. Which brings us to the second form of decrypting GSM traffic. That would be to just listen in on a communication that happens between the real handset and the real base station, and trying to decrypt that later on, or as close to real time as possible, in fact, given an FPGA cluster as a couple of companies will sell you exactly for this purpose. Now this talk will show you the details of what happens inside of this cluster and what happened towards building this cluster, and propose a distributed network that should take over the functionality of this expensive cluster. So we can, in a joint effort, publicly show that really any GSM conversation can be decrypted given sufficient resources. Sounds good so far? If there's any questions throughout, please jump in.
These active intercepts, that's an IMSI catcher, isn't it?
Right.
You say it's easily spottable. Is it spottable by the victim? By the mobile phone itself? No.
The mobile phone could display that no encryption is being used, for instance. In fact, all phones support that technology, that functionality. They are obligated to through standard, but that functionality can be deactivated through the SIM card, and all carriers actually deactivate this functionality. So while your phone could tell you you're under attack, your operator doesn't want you to know for whatever reason. Perhaps because half of the carriers in the world don't use encryption, and the operators don't want to scare their customers as they're roaming through different countries. But yeah, you could spot this. If you pay attention, if you overwrite that or ignore that bit on your SIM card, your phone will tell you you are under attack.
So you have to have control over your phone, and I think 99.something% of all people using phones don't.
Right. You have to be aware of this happening and have to pay attention yeah. Another point where this could be detected at is by the real network operator. This attack, of course, relies on the fact that you can spoof a network operator within their domain. Now, they can detect that, but, well, they either don't, or they choose to ignore this, since most IMSI catchers are operated by law enforcement. And what are you going to do if you notice that the police is pulling off a law enforcement operation? And you're going to call the police and notify them about it. Yeah. So they choose to ignore it. Yeah, but we'll be focusing on the second, more elegant solution of breaking GSM. Now, having talked about the attack goal a little bit, here's just a few applications that have been popping up over the last years that are built up on the assumption that GSM is a secure technology, and in particular, text messaging is secure. The last talk should have clearly stated that that's not the case on an application level, but even if you were to fix all the application level bugs and the architectural routing flaws in the network, GSMs can still be decrypted. Another big area of where GSM is used as a trust anchor are mobile RFID applications. NFC is what the technology is called, the RFID technology when it moves into a phone. And good RFID tags use cryptographic keys, of course. Now, if you want your phone to be emulating a good cryptographic RFID tag, it needs to learn the cryptographic key, and that is usually being sent over GSM to seed the phone. So while it can be stored very securely in a secure element on the phone, the way it's getting to the phone is usually insecure. Well, so this just as additional motivation why you would want to stop the belief that GSM is secure enough. Let's talk about the attack we're going to pull off. It's a generic time memory trade-off attack that bases itself on the idea of a codebook. A codebook being a generic tool to break small ciphers with small key sizes. It works pretty much like a phone book, say, where you have two data columns, long lists of two data columns that in this case map the input to this cryptographic function, that is secret, of course, to the output, which you can absorb over the air. If you had this phone book and you sorted it by the second column, the output, you can, based on something you see on the air, look up the secret information that went in computing it. Now, this works against all ciphers with small enough keys. A51's key is not small enough for a normal codebook attack to work. In fact, if you were to just compute this codebook entirely, it would be somewhere in excess of 100 petabytes. And I don't think anybody is willing to spend that many resources just on breaking somebody's call. Also, computing it in a very straightforward manner by crunching A51 computations on a PC will cost you something in excess of 100,000 computing years. So again, nothing we would be willing to spend just to show that this technology is weak. So what I'll be focusing on next is show how this codebook can be stored smaller and computed faster, which is all we need on the cryptographic side to break A51. The steps I'm going to walk you through are, first, we need to be able to compute A51 much faster than the straightforward way on the CPU. We're talking about a couple of techniques we applied there on different technologies, on different platforms. I'll then be talking about how to best store this data in what's called rainbow tables and how to best parameterize those. Since I think we found the best trade-off so far for all the rainbow table efforts that have been conducted on A51. And then finally, I need your involvement in executing this set of tools we have produced that will produce the tables needed to crack A51. We'll be talking about that later, though, and I'll tell you exactly how you should get involved. So first up, how do we get A51 to compute a lot faster than we initially thought was needed to break this? Well, first, one piece of knowledge, A51 is highly efficient in a dedicated hardware implementation. It uses a lot of shift registers and things like dynamic clocking, which is trivial to implement if you build your own chip. And nobody's going to build a chip to help us crunch these numbers faster. So the best we can hope for is a platform that is as close to dedicated hardware as possible. That would be an FPGA, or at least simple enough to execute lots of small instruction in parallel. That would be a graphics card. So instead of deploying this to CPUs, we decided to optimize it for both NVIDIA and ATI graphic cards, as well as Vertex FPGAs. So starting at our 100,000 computing years, we first parallelize it massively. That's where you get in. So we can now distribute the load across many people and have each of you compute a little part of this. A single GPU internally has hundreds of compute kernels that can each crunch an A5-1 computation. Now, if several hundred people with several hundred cores into their one graphic cards execute this in parallel, we're already down to some 1 year. We didn't stop there, though. We wanted to further tweak the algorithm as much as possible to specifically fit the computing resources we have here. And I'll be doing one technical deep dive into exactly how we optimized it for CUDA, where we don't just have all these compute kernels, but also memory. So we didn't want to have that memory go spare. And then finally, and this is just happening this week, we started rolling out our bit sliced implementation, which I had no idea could give us this good of a speed up. Bit slicing being the idea of computing the same instruction on a lot of data segments. So the MMX or the SSE and Intel processors. So the CUDA card, for instance, gives us the ability to execute the same instruction on 64 data items at the same time. Intel even goes up to 128. And with just porting it to bit slice, we get another performance tweak of a factor of 3 to 4, depending on the platform. So we're still shocked to find that we can further and further and further tweak it. At the moment, we're running about 5 times faster than when we first released this software in the summer, which was already highly optimized. Yeah, so we're down to requiring just a few months on a reasonably small set of ATI or CUDA nodes. Say you had a PlayStation 3 cluster, as for instance some universities do, you can compute this whole set of tables in just 1 or 2 months yourself. So doing this quick deep dive into how we optimize A5-1 for the CUDA card, for those of you who are interested. A5-1 is composed of a state of a total of 64 bits spread over 3 registers. And all the registers marked in either orange or green here determine what the next round will look like once all these shift. Meaning that if you knew all the bits in the colorful boxes here, you would know what the next 4 rounds look like, since these are all the bits after shifting that would determine the next rounds. Now, instead of doing one shift at a time, as the hardware implementation, the optimal hardware implementation would do, on CUDA we make use of the fact that we have lots of memory, really fast memory too on these graphic cards, and we compute 4 bits at a time by having large lookup tables that, based on all of these bits, determine what the outputs are, what the clocking decisions are, and what bits we need to shift into the LFSRs. Since we can squeeze in these table lookups just in between our shift operations, we get a speed of almost a factor of 4 by using spare resources that otherwise would have gone lost. Similar idea applies to ATI cards, and if you further bit slice, you get an additional factor of 3 improvement. So all of this is to tell you that cryptography often can be broken much faster than the obvious computational complexity would suggest. Still, I don't think the whole idea of brute forcing a significant part of a key space does extend much beyond 64 bits. So ciphers with much larger key spaces, say AES, even a triple DES, are not at all affected by this. You can optimize the hell out of it and still take hundreds of trillions of years. So yeah, that was the one technical deep dive I wanted to do with you, just to show what type of optimization effort went into here. Now here's the second deep dive. A little discussion on how these rainbow tables work, what we actually do compute in order to decrypt or find secret keys for that matter. We were talking about the code book before, in which you find the secret information by just looking up what you found as the output, as the data that's going over the air. That approach, we said, wasn't going to scale since we can't compute the whole code book, or at least not entirely store it. So here's an optimization, how you can store a code book much compressed. Instead of computing just one hop from one input to one output, you're computing a whole chain of input-output iterations. So if you're starting at any random number and you play the A51 function, you treat this, the output, as the input into the next A51 computation, and so forth. And if you do this a couple million times, and you store only the first and the last row of this table, you get your storage requirements down from petabytes to a few gigabytes, at most terabytes, depending on your trade-offs. Now, what do we gain if we just store the first and the last column? Say that the value we were observing on the air was the 49A6 down here. Now, in the normal codebook, we would try to look up that value in our stored codebook, which is the yellow column in here. But in this case, we won't find it. We now apply the A51 computation to at once get this value, and again, try to look it up in our codebook in the yellow column. Again, don't find it. We apply A51 once more, and there it is. We find it in the yellow column in our compressed codebook. We know what chain the right value would be in, and we start at the beginning of the chain, computing A51 until we again hit the value we were observing. Now we know one before that is the secret key we were looking for. Does that make sense? Now, there's a couple of drawbacks to this technique. It works great for bringing down the storage requirements. It doesn't actually work in practice as an attack tool, since if this is a million links in a chain, you'd have to do 1 million hard disk lookups just to decrypt one packet, which is time-wise much in excess of the attack time we're targeting. So we need to further optimize it. And luckily, there's some academics who thought about this a while ago. Two techniques I want to introduce, and then tell you how we combined the two techniques to find what we think is the optimal time-memory trade-off for A51. So here's the first technique. Instead of computing all these chains with equal lengths, you have a defined end-of-chain criteria, which could be, for instance, half of the bits in your, the last half of your bits being 0. So you terminate every chain at exactly this end criteria. They'll all be of different lengths, but you can statistically cut off at some point and not lose too much computational energy. So if you do now, again, start at any value that you observed in the air, you compute A51s until you hit a value that matches this criterion, and only then do a hard disk lookup. But this is the first optimization that helps us speed up the attack tremendously by getting away from the hard disk bottleneck. The main problem with this optimization is that it introduces lots of collisions. Collisions being the case where if you ever see the same value twice in your chain, well, actually, these should be the same values. If you ever see the same value twice in your chain, up from this point, the two chains will merge, and the next values will all be the same since you're doing the same operations. Now, the longer your table is, the higher the chance that the next chain you're introducing will collide with an already existing chain, of course. So this puts an upper limit on the height of these tables. That upper limit, for any practical sense, being much lower than the size of table we need. So we have to start with a new table with a slightly modified function and more and more and more tables. And the attack effort, of course, scales linearly with the number of tables. So collisions are a huge problem here that limit our ability to make best use of this optimization. Now, there's another optimization, of course. Academics are usually a couple of decades ahead in cryptography that help us get rid of collisions almost altogether. And that now is what's called the rainbow technique. Rainbow because now in your chain, you have a different coloring of every link going through all the colors of the rainbow, if you so wish. And these different functions, the different case here, can still all be derivatives of A51. The difference could be as simple as XORing a small number into the A51 input, but it still makes it a distinguishably different function. If you do compute tables this way, where you have on every link a different function, if two values do collide, they'll not lead to chains merging, since the next function will, in all likelihood, be different, since there's a million different functions. Does that make sense? I'm almost done with the deep dive. Just wanted to give the engineers in the room little stuff to think about. Now, what we did is combine the two ideas, of course. We want both little hard disk load and little collision, so we can store our data in as few tables as possible. The optimization, the point in the trade-off curve that we do choose was to do a distinguished point computation, not once, but 32 times, and each time changing the function in the rainbow manner. So we are hitting the distinguished point criteria a total of 32 times, and only then after that call it the end of the chain. And again, only store the very beginning and the end. Now this point in the trade-off curve might look arbitrary to you, and it somewhat is. There's a lot of assumptions that went in. Made assumptions about how much storage we want to spend on this total. Should be something, at least we figured, that could be hosted somewhere kind of cheaply, a few terabytes. You have to make some assumptions about how much plain text you know in a transaction and what success rate you want to get out of it. Now, these numbers just went up kind of a lot after talking to David Burgess, who gave us some additional ideas on where to find known plain text. So if you do have some control over the data in the network, meaning you are a subscriber to the same cell, which just means purchasing a prepaid SIM card, then we are, with our setup, up to close to 100% success rate, assuming though that we have very little transmission errors, which we can't detect on this level. So we'll just assume that the data we're getting is good. On a more realistic assumptions, with a little less power to the attacker, we're still at about 50% success rate, which is the target for our public proof of concept, already assuming some transmission errors and all that good stuff, which would then allow us a close to real-time decryption, or at least a close to real-time break of the key, which then allows you to go back and decrypt the entire conversation from when it started. So yeah, these assumptions lead to exactly this configuration. There's some discussion about this going on in the mailing list if you want to follow up or want to throw in your ideas. So that was the deep dives. Now, if you do want to get involved, here's what you want to do. Download the software, of course. The source code available, everything is open source, but there's also binaries for both Linux and Windows. I think Mac OS is in there somewhere. Run them for a couple of weeks until you have the first table generated. and then start sharing the table. Preferably just bring him to Hacker Conference. If you don't happen to come to 2633, use our private BitTorrent tracker. I can give you a lock-in to it as soon as you have your first table. And then we'll introduce some redundancy as much as possible, again, to shield this effort from external interference. So nobody's really running any critical infrastructure. This is all happening distributed. But at some point, we will want to coordinate on showing that this is carrying as just a community effort. Also, get involved by signing up to the mailing list. There's both cryptographic discussions going on in the mailing list and very practical programming questions, how to further tweak this. Good stuff. I learned a lot through just the discussions on the mailing list. Now, before giving you the actual nugget out of this talk, let me quickly wrap up this part of it. So we want to, of course, not just stop at A51, but make this a more general tool of attacking cryptographic primitives that don't have a sufficiently large key space. If you have any cipher that you think matches this criterion, anything proprietary, perhaps, get in touch with us. We'll be happy to port it for you to this framework. It's extremely generic. It has a lot of backends. Even Intel, if you so choose, if you're not paying your electricity bill yourself. Yeah, and we'd be happy to extend the tool. Also, if you want to help us optimize, port, or tweak this in any other way, please get involved. This is a very open effort, and we definitely need not just your compute cycles, but also your insights as users or perhaps developers of such technologies. Now, we'll have this done by the end of the year, most likely. As much as this is an anonymous effort, we are getting some feedback and tables are being computed. And if some of you get involved too, we should be there having all these tables done by the end of the year. If you don't want to wait breaking A51 until then, here's another attack that I don't think has been talked about much before. It's an attack with some more restrictions. On the other hand, it's very easy to pull off. Here's how it works. You record a call as it's happening between a phone and a base station. You just recorded it, not being able to decode anything. You might need a wideband receiver if there's a lot of hopping going on, but this is definitely feasible. You then, after the call has terminated or after the SMS has been received, force the phone to subscribe to your own base station. You initiate another channel, you start another channel with this phone, this time telling it to use the weak A52 cipher. A52 was intentionally weakened, so it could be exported to Eastern countries and that. So you force it to use this A52 cipher, which is still present in a lot of phones. And without you even knowing the key that the phone is going to use, you're not telling the phone anything further. The phone starts sending you idle frames. It will ask you, is there anything, is there anything, is there anything? It will just tell you that it's still alive and sending on this channel, but it will do so encrypted. It will take known plain text and encrypt it under a weak cipher, right? If you did choose the same random number in the key establishment, it will use the same key that it did before use to encrypt something with A51. Now, after you collected a few of these idle frames, you run a cryptographic attack on A52. It's very well documented. It has been broken academically a while back. And you just found the key to decrypt the conversation you sniffed earlier. Now, this attack, very straightforward, doesn't take a lot of equipment. All the parts are already available. It's not quite as elegant since it's not passive. You have to wait till the call terminates and get close enough to the victim to force him onto your base station. And it might not work against newer phones, since A52 is supposed to be phased out for a while now. But it is still in a lot of phones, I can tell you that. Now, here's the tools you want to use to pull this off. You want to use AirProbe, an open source project. that runs on a USRP to record the data. You want to use either the OpenBTS or the OpenBSC, again, open source projects, to emulate your fake base station and pretend you're T-Mobile or AT&T, so that the phones are attracted to a base station. You want to use Börham's attack to break the A5 in just a few minutes on your computer, and you then decrypt the call again using some open source tools from the AirPro packet. So there was one component missing, that is a way of telling either the OpenBTS or the OpenBSC to start ciphering and ignoring that it doesn't actually have the key. Meanwhile, the phone feels obligated to send the idle packets. Now we did add that component last night, so should be in the SVN for Open BSC. Harald, maybe already, maybe soon. It's in the Git already. So DeepSec 2009, build your own A51 cracker if you so choose from just one or two USRPs and a little cryptographic insight. I think with that, I'm pretty much at the end of what I wanted to tell you, but I'd be very happy if you had some questions and we could start a little discussion here. So with that, thank you very much.
Now we've got some time for questions.
Hi, are you legally going to be able to show this proof of concept, to demonstrate it?
Probably not against a real carrier, but we can run our own networks in the test frequencies we were, for example, allocated here. So I think that would be legal, yes.
It's possible to get frequencies for testing use. That was done on the last CCC, I think, on the Communication Congress. They got from the German authorities a frequency to test and used the OpenBSC during the whole conference. So yes, I can say this is legal.
Yeah, well, if you're worried that people won't believe that this is actually practical, if we don't actually do something illegal, then I must say these people are illusionist believers that laws will prevent criminals from doing crime.
More questions?
Can you name a percentage number in how far the tables are computed on your BitTorrent tracker?
Well, it's all anonymous, right? So we don't know. All we do know is we have lots of tables already, and with that additional insight into known plaintext packets that David gave us here, we already have a working exploit with some success probability. All that's needed now is to bring that over some critical threshold where people really appreciate it as a threat rather than a technical possibility.
More questions?
A question about the notification of the encryption disabled and enabled on the GSM network. Is there a simple AT command to re-enable the notification?
I don't think there is, since the phone is really obligated to do what the SIM card tells it. There is, however, SIM proxies that you slip just in between your SIM card and your phone, and you could use that to flip the bit. So yeah, it's not elegant. You'd probably want access to some phone's firmware to patch that out of it. Or you get some phone that just ignores functionality like that, since like the crypto phone.
Okay, so it would be possible with a SIM card reader writer to modify this setting?
You can actually overwrite a bit, it's locked, but you can change it as the SIM card is being queried for it. Yeah. It's a little clumsy, but at least to figure out whether in the country you are in at the moment they use encryption, that would be a straightforward way to do it.
You mentioned earlier in your presentation that intelligence agencies, law enforcement, and criminals are using this technique. Now, obviously, for the first two, we know that's true, and for the criminals, we know they definitely want to, but is there any publicly available evidence of where criminals have used GSM cracking for real-world crime?
Good question. I don't know. So if they snoop around on the internet a little bit, they'll come across advertisement material for such boxes pretty quickly. So if there was a well enough funded criminal organization, they could quickly buy stuff like this. It comes with really nice GUIs to see all the calls that are going on, all the SMSs. So this is available on the market. It's illegal to operate, but if you're already a criminal, I don't think you care very much.
More questions?
Now let me ask a question then. What should the network operators do to mitigate this threat? Since we just in the second attack here showed that this is so easily broken. Well, of course, they should go to a better encryption. And fortunately, the GSM Alliance a few years back was proactive about it and proposed using A5.3, the yet better encryption that's used in 3G for GSM. A lot of phones already support that. I think my BlackBerry does. But no network in the world that I know of does support it yet. So now it's up to the network operators to upgrade their systems to the 21st century, enabling people to use a standard encryption that any 3G user already gets to use, but GSM users don't. So it's really up to the network operator. One note though, this very attack where you replace one cipher with another and break the easier one also works against A5.3. So really what you want is a phone that only ever uses A5.3, which of course breaks all backward compatibility. So that doesn't seem to be a quick fix. First step would of course be to enable users to use A5.3 and give them a notification on their phone when that's actually the case, right? But as I said, no quick fixes here, unfortunately.
And that attack also applies once A5.2 is cracked, A5.1 is cracked, can be used for A5.3 using A5.1 as a weaker cipher.
Exactly. So I don't think there will be very many phones that speak both A5.3 and A5.2, since the one is supposed to be phased out while the other one is being introduced. But as soon as you can break A5.1 clearly, you can substitute A5.1 here and A5.3 here, exactly. Yeah, so this attack still carries.
I'll come to you soon. Any comments on the lifetime of GSM base station equipment? Because this really depends on how long this lifetime is. So I don't see that operators will phase in new equipment soon.
I would have thought that's the case, but even new equipment doesn't have A5.3 by default. It's a very expensive upgrade by the network operators that you could, in theory, though, roll out to old equipment as well.
Okay.
It's just a matter of investing into security, not a matter of getting rid of old equipment in this case.
I did not understand because why a same random gets the same key even if you change the underlying cryptographic system. I might miss something on A5.3. It might be the same designer's decision to use the same key generation scheme, but it's not necessary, or?
Well, the key is not generated by A5.1, 2, or 3. The key is generated by other functions. They're called A3 and A8 on the SIM card. And every SIM card implements them exactly once. It will always use the same mapping from a secret key KI and a random number to key KC that's actually being used here. And only after that it starts using A5.1, 2, 3.
And the key is dictated by the base station in that case, in the
The
protocol.
random number is sent by the base station.
Okay.
So we can control this. And it's sent in the plane before, so we can read it. So it's really trivial to make it the same. Yeah. Well, try it out if you have 2 USRPs. You can break your own phone calls. Don't try it on a real network, it's illegal.
Yeah, then if there are no further questions, but I think you will be available during the coffee break, so let's start the coffee break, and thank you very much.
Thank you, guys.